Hi, this is David from UCR Supplemental Instruction, here again to talk to you about Physics 40B, and this time about something that might seem a little bit random, but it does fit into the content that we're talking about lately, that being calorimetry. So calorimetry is, well, this fits in because it's a pretty raw expression of the first law of thermodynamics. Earlier, we expressed that as the change in energy of a system is equal to the heat or energy by heat added minus the energy by work removed. And so that remains true, but that's not what we're going to be using here. Instead, it might be more helpful to look at the more wordy definition, that being that the energy or energy cannot be destroyed or created. So for a system like this, if we're assuming, no heat is added by other sources, essentially, this gives us a governing equation for calorimetry problems. So we can say that the energy stored in one of these masses and the other mass and the other mass, regardless of where that goes between the masses, that amount of energy is always the same. So these are how most of your calorimetry problems are going to look. You have some water here, and you have two other objects. We're assuming they're solids. The water is at some initial temperature, which I've marked as TWI, W for water, I for initial. And then these two objects, we don't know what they are, we'll just call them 1 and 2, have the following. So there's T1I for the initial temperature of this block 1, T2I for the initial temperature of block 2, M1 for the mass of this block, M2 for the mass of the second block, and C this time is the specific heat, but unlike last time, it's not on a molar basis, it's on a mass basis. So the primary equation we're using for this will look similar, and actually I think we talked about it in the last video, is that Q equals MC of the T. So let's make this a little bigger. This is pretty much the only equation that we really need for all of this. Now you might remember this looks similar to Q equals N, as in November, C times, or capital C times delta T. And that's essentially the same equation, just on a molar basis. So now we're doing this in terms of mass. We're given masses. It would be equivalent to do the same thing, but given moles, but this is more common. So we'll have units of kilograms, presumably, for M1 and M2. All right, so knowing that, and knowing that due to the first law of thermodynamics, energy cannot be created or destroyed, how do we go about solving this problem? Well, if energy is not created or destroyed, the only energy that is entering the system, and if we want to sort of claim that the system is everything here, this is our entire system, then if energy isn't created or destroyed, the energy that is held within these two blocks at their initial states and the energy that is held within the water at its initial state should be the same as the sum of the final energy that we have after the system comes to thermal equilibrium. And that means that the temperature of everything is equivalent. So if you have room temperature water and you put, a hot block of copper in and a cold block of aluminum in, if infinite time goes by and we assume that no heat is lost to the environment, then after that time, all of these objects should have the same temperature. So that's what we're looking for, a common final temperature. All right, and so now let's get into the actual equations here. I'll remove that for space purposes. All right, so we're using this problem. Now Q, to be clear, this is not how much energy is held within anything. This is rather how much energy is moving between two different things. Remember, we have a delta T here, that's a change in temperature. So this is specific to a certain process. All right, so let's start describing this. And again, applying to the first law, the total change in energy for the system, like we said, is 0 because energy is only moving between things within it. So we can start there. dE is 0. Okay, that's not helpful on its own though. But what that also means is that the sum of all these energy transfers, again described by Q equals MC delta T, is 0. And because that's our total change in energy. So we would have 1 times C1 times, and we'll use TF to describe the final temperature, minus T WI. And then same thing for, it should be CW and CW for the mass of the water. You need to know how much water you have and the specific heat of water. So continuing then, M1 times C1 times, and now instead of, well, remember that the final temperature is common, so there's no need to differentiate between the two. But we'll have T1I And then the same thing for our last mass, M2 times C2 times, again, same thing, TF, but T2I. So this describes all of the processes here, and this adds up to 0, so we know that some of these terms are going to be negative, and the negative ones will just be the ones where the initial temperature is higher than the final temperature that they equilibrate to. So let's say we want to solve for the final temperature. That's a fairly common way to go about these problems. At this point, it's kind of just tedious algebra, right? So we can distribute in each of these terms, mW times CW times TF, so we can separate that out. And then I'm going to sort of skip steps here because it's a lot to type over and over. Let's see, mW times CW times TF. I'm going to keep this on one side of the equation, plus M1 times C1 times TF. Plus M2 times C2 times TF. So this being 1/2 of our equation, let's expand this. And then, well, if we split this up, we have a negative here, so we would have negative MW times CW times TWI, T1I, etc. So we can move that to the other side of the equation. MW times CW times TWI plus M1 times C1 times T1I, and then, of course, the last term. So you can see why this is kind of tedious, but this is, well, once you've done it a couple times, you'll be able to start skipping steps and get it done a lot faster. Right, so again, just splitting it up, we distributed the mass and specific heat to each of these terms, and then just move the negative terms to the other side of the equation, which was still equal to 0, as we saw before. All right, so now you can factor out the TF out of each of these terms. So you have it on one side, and you can divide all this under the other side. So it's a lot to plug into a calculator, but it is essentially just algebra, so not a whole lot to worry about there. And it's as simple as that, though. Even if you want to go back and solve for a different term, maybe they want you to solve for the initial temperature or the mass of something, that's also common. The practice is pretty much the same. It's just an algebraic rearrangement of the sum of the energy transfers. All right, so that's all for today. Hope you learned something, and I'll see you next time.